So yesterday we started talking about circular motion, and we said that some of the basic principles involved with circular motion are that in order for something to travel in a circle, it has to always be doing what? Accelerating. Where? Which direction is that acceleration? Towards the center, right? That's centripetal, center seeking. Okay, so centripetal acceleration has to be present in order for an object to move in a circle. That means its velocity is always changing, even though its speed is constant. Okay, kind of contradictory. It can travel at a constant speed because speed is scalar. Okay, but its velocity is always changing because the direction of travel is always being altered by that force pulling it towards the center. Okay, causing that centripetal acceleration. All right, so we're going to look at kind of how that works. Obviously, in order for an acceleration to be present, there has to be a net force. Okay, we learned that in the last unit. Okay, that net force is the centripetal force. Okay, so all the forces that are acting, okay, on that object have to have a vector sum that points towards the middle. Okay, now, don't get the idea that there's going to be a whole bunch of like weird angled forces or anything like that. There aren't. Okay, like the most complex thing we deal with are forces in and forces straight out. Okay, and that's only when we get to vertical circles. For uniform circular motion, we only deal with forces going into the middle. That's it. Okay, that's all we have to worry about. Now, there's lots of different examples of centripetal forces. Okay, things that can push an object towards the center. Okay, now it might seem weird. Like pull seems obvious, right? Like you got something whirling around on a string pulling towards the middle. Okay, gravity pulls the moon towards the middle of the earth. Okay, those are pulls, those are obvious. Can you think of any situations where there might be something that pushes towards the middle? Anybody ever ride the Gravitron at Stampede? Yeah. Spins around and around and you can stick to the wall. Okay. Okay. They kind of put you in there, but you can lift your feet up, you don't fall because it's spinning around and around really, really fast. Okay. What they're doing there is they're using your inertia, which wants you to leave the circle. Okay, like this arrow is showing here, the red arrow. Okay, your inertia wants you to go like this, but the outside wall of the ride pushes you back towards the center. Okay, and if you get it spinning fast enough, that force becomes greater than the force of gravity, and then as a result, you can't fall, you can't fly out, okay? And you could even, if they let you, stand on the wall, okay? And you would be horizontal, but spinning around and around, okay? Yeah, it's, how many people have ever been on the Gravitron? Okay, but they don't let you do that, okay? But I have this really cool video of the guys that actually run the ride doing that, okay? As they're allowed. So the physics of that sling, okay, is that if you've got a rock in the sling, sorry. Yeah. No. Okay. The physics of the sling is that you can get that rock moving a lot faster in the sling than you could if you just threw it. You're increasing the radius of the circle. You're making your arm longer. Okay? And because you've got this material, okay, in there that's, you know, able to be essentially swung in a big circle, okay, you can get that going really, really fast. Okay? So much so that what they said in the video is true. If you've ever heard a whip crack, that's the end of the whip breaking the sound barrier. That means it's going faster than 340 meters per second. Okay? So the rock, when it leaves the sling, is traveling nearly that fast. Okay? And when that would hit you, okay, and I mean, we're not talking about a little rock. Okay? These were, you know, rocks from a river. Okay? They would have been, you know, fairly large, smooth, so that it would have flown through the air. Okay? And if that hits you in the head, it causes a skull fracture, and then usually like a subdural hematoma, which is a brain bleed. Okay? So that rock hits him right here in the forehead, which is the only spot his helmet didn't cover. There's a design flaw. Okay? But it didn't cover that part, got him right there, okay, and fractured the skull, which not only then puts fragments of bone, obviously, into the brain, but it's just like a concussion. It causes a wave to travel through the brain, and the back the brain travels, right, and it kind of bounces off the inside of the skull, which is what causes a concussion, okay? If you get just a minor concussion, you might get a slight bit of bleeding in the brain, but mostly bruising and inflammation. That's what leads to all the post-concussive symptoms, okay? But in something like this, with a skull fracture, okay, we're talking about arteries within the brain being broken and bleeding out. So then the brain starves, doesn't get oxygen because it's bleeding out, and the person dies, okay? So that's essentially how that worked, but it worked by using this idea of circular motion to increase the speed and destructive power of that rock, okay? More so than a bunch of Israelites throwing rocks could have ever done. All right, so in order to get this to happen, we have to have a centripetal acceleration and a net force, okay, that is directed towards the center. So with David's sling, it's the sling, okay? The sling is holding the rock in the circle. It's exerting a force that's preventing the rock from going in a straight line until it gets released. Okay? Now, if you've ever seen what a sling looks like, it's got like a circle on one end that goes around your finger, okay? And then the other end has a knot, and so it makes a loop. Okay? You hold the knot, and the loop goes around your finger, and then you whip it around and around really fast. And when you let go of the knot, okay, that's at the moment that that happens, that's the direction that the rock will go. Okay, and then it will be moving very, very fast. Okay, it was obviously just used by shepherds, which is what David was at the time, to kill predators that would be attacking their flocks, so bears and lions and stuff like that. Okay. All right, does that make sense to everybody? Okay. So the same thing happens with the Earth and the Moon. Okay, there's a gravitational attraction that we'll talk more about later in the unit. Okay, that keeps the Moon in orbit around the Earth. Now, for today, we're going to simplify that. The Moon orbits the Earth. In actual fact, they both orbit a point that is just slightly under the Earth's surface. Strange but true. Okay? They actually kind of orbit a common central point that is not the Earth. Okay? But we're going to simplify for today. The Earth exerts a gravitational attractive force on the Moon that holds the Moon in orbit. Okay? And the Moon just goes around and around. All right? Now, that's not a perfect circle. It's an ellipse. And it's getting bigger all the time. The Moon will eventually be lost, but don't worry, it's not going to be tomorrow or even next year. Okay? We're talking like maybe right before the sun envelops the Earth, okay? As it goes, becomes a big giant. But it does exert that gravitational force that holds the Moon there. Okay? Now, the Moon also exerts a gravitational force on the Earth. Okay? We know that because we see it. Where do we see it? Yeah, in the water, the tides. Okay, the tides are caused by the gravitational attraction of the Moon. The whole ocean is pulled toward the Moon. Okay. So with our centripetal acceleration here, okay, we see that an object that's going in uniform circular motion would fly off on a tangent, so in a straight line, if that centripetal force was absent or suddenly released. Okay, and then move in that straight line. So the object accelerates towards the center. At every moment, it's moving in the circle, okay? And we call that centripetal because it is center seeking, okay? All right. Now, yesterday we talked briefly about the effect of radius, okay, on this. So if I've got two cars, two corners, same car, and it's moving into the corner at 28 meters per second, okay? On which one of these corners are you going to feel more thrown to the outside? Small. Yeah, exactly. Okay, and that's because of this. Centripetal acceleration is v squared over r. V is the same for both of these corners, but on the first corner, r is small. So we're dividing v squared by a small number. That means there's a large centripetal acceleration. Okay, on this corner, r is much bigger, so we get a smaller centripetal acceleration. Okay, that's why race car drivers take corners really wide. Okay, if you take a corner really sharp, you're more likely to lose traction and slide. Okay, and your passengers are more likely to be gripping the holy crap bar, okay, and praying for their lives. Okay, you know what I mean, right? Handle on the door. Okay, and this is where also, if you're one of those people who drives a Jeep that doesn't have doors, okay, if your passengers are not seat belted in, they will exit the vehicle through the door. I've seen it happen actually. Okay. It can totally happen on that. It's also one of the reasons, I mean, among thousands of reasons, to wear your seatbelt, right? If you were to roll, okay, in rollovers, what kills people that are ejected is their own car. Okay? Because as the car rolls like this, okay, when do you get ejected from the car? Always the top. You can't be ejected from the bottom, the ground is there. Okay? So your inertia is always to try and leave the circle. So almost every time you're ejected right here. Okay? Okay? You're ejected right here. And because then you're ejected, you become a projectile. Car rolls over you. That's what usually happens to someone ejected from a rolling vehicle. Okay? They follow Newton's first law, they go this way, but then gravity kicks in and pulls them down as a projectile and they land in front of the car and get rolled over.
I've like banned my dad from driving golf carts because every time he drives, he takes the corners so sharp and I always get thrown at me. So he's no longer allowed.
He's no longer allowed to drive?
He's banned.
Yeah. Yeah, take them either wider or slower, right? Make it comfortable for your passengers, safe for your passengers, okay? Radius has that effect, okay? So the wider the radius, the less centripetal force is required, okay? And the less thrown to the outside your passengers will feel, right? That's why typically we have on exit ramps, we make the corners as wide as we can, okay? The wider the corner, the safer it's going to be. Now, some cases, obviously, space is a factor. We have to make them tighter, so we make the speed limits on the tighter corners smaller. All right, so if we're looking at that mathematically, okay, we can see that for the radius of 320 meters, we've got 2.5 meters per second squared as our acceleration. That's pretty high, okay? That means that if you weigh 200 pounds, okay, you would feel 50 pounds worth of force from the door. Okay, if you went into the door on a corner like that, you would feel 50 pounds worth of force pushing back against you. It's 1/4 of a G, 1/4 of gravity. Okay. And then for the radius, 960 meters, okay, so 3 times bigger radius, we got 3 times less centripetal acceleration. All right. Okay, so in question number 2 here, they want us to identify the force that's acting as a centripetal force in each of the following situations. We've talked about, I think, all 3 of these. If you take a turn, take a corner in a car, what keeps you in the corner? Friction. Yeah. Static friction is what keeps you in the corner. If you start to slide, then you're depending on kinetic friction. Which one did we say was always bigger, static or kinetic? Static. Yeah, static friction is always bigger. So when you turn a corner, as long as you're not sliding, you're relying on static friction between your tires and the road to act as a centripetal force and push you back towards the center. Okay. Ball tied to the end of a rope. What's acting as a centripetal force there? Oh, sorry, I think we had it. Yeah, the hand or the rope, whatever's connecting the 2 things. Okay, the tension probably in the rope would be the thing that's pulling the object back towards the center. Okay, and then the moon moves into circular orbit. Gravity, yeah, force of gravity is acting as a centripetal force. Gravity acts as a centripetal force for lots of things. Okay, not just the moon in orbit, but for a lot of things even on the Earth's surface. Okay, all kinds of vertical circle types of situations. If you've ever gone over the top of a hill kind of fast on a road, okay, and you got that feeling like your stomach was kind of moving up into your chest or into your throat, okay, that's because gravity is acting as a centripetal force. It's why projectiles always follow an arc. Okay, gravity is acting as a centripetal force that's bringing them back down, so they travel in a circular pattern. All right. So that's all there was for that one. So talk about centripetal force next. Okay, so talking about centripetal force, all we talked about in that first lesson was just an object goes in a circle, here's what that looks like, here's why, okay? Now we're gonna look at how those forces that keep it in the circle work, okay? So we know if an object's moving in a circle, it's traveling at a constant speed, not a constant velocity, it's always accelerating. Objects accelerate because there's a net force acting on them. Net force and acceleration are always in the same direction. That's all stuff from last unit. Still applies here. In order for something to move in a circle, it has to accelerate towards the center, which means the net force has to act towards the center of the circle, and that net force in this unit is centripetal force, center seeking force. Okay? All right, everybody okay with that idea? All right, so this is what I was saying just a minute ago. Newton's second law says whenever an object accelerates, there has to be a net force that is creating that acceleration, okay? And that's also true for circular motion, okay? We just write Newton's second law differently in this unit, right? Newton's second law says that net force equals mass times acceleration. Well, in this unit, okay, the net force is the centripetal force, and that is mass times centripetal acceleration. We were just looking at that formula a minute ago, AC equals V squared over R. Okay, so this is really M times A for an object moving in a circle. Okay, it's still Newton's second law, it's just applied to a circle instead. Okay, that's what we got right there. Everybody all right with that idea? Okay, so this is kind of the strange thing is when we're looking at all these real world situations, we have to understand that that centripetal force always acts towards the center. It doesn't matter what the car or object is doing, okay? It's constantly being redirected by that net force, by that centripetal force, which is what makes it travel in that circular path. Okay, so in lots of cases, identifying that circular or centripetal force is easy because it's obvious. We can see it. Okay, if something is tied on the end of a rope, we can see the rope pulling the object back towards the middle. Okay, but in some situations, it's a little bit tougher because we don't see the physical connection between the object and the center. Like when I asked you what keeps something moving in a circle as it travels, like when you're turning a corner. Okay, you don't see friction per se. Okay? There's not a physical connection between the center of the corner and the car, okay? But there is a frictional force that's keeping the tires from sliding in a straight line, okay? It's pulling the object back towards the center, but it's harder to identify it in that situation, okay? All right, so in this case here, okay, we've got a model airplane and we want to calculate the centripetal force for two different speeds, okay? A speed of 38 and 19 meters per second. So just a minute ago we said centripetal force is mv squared divided by r. Okay? So what we want to look at here is what's the effective speed on centripetal force? According to that formula, as speed increases, what should happen to centripetal force? It should what? Okay, if everything else stays the same and V gets bigger, what will happen to FC? It'll increase. How? Linearly or exponentially? Exponentially. Okay, as soon as V starts getting bigger, because V is squared, it'll cause an exponential increase in FC. Right, so I'm looking at 19 and 38 meters per second. 38 is 2 times bigger than 19. So when I calculate my centripetal force, the centripetal force at 38 will be 4 times bigger. Okay, so let's just double check that that's the case. All right, so FC for the 19 meter per second one. All right, so that's going to be 0.9 kilograms was our mass, okay, multiplied by 19 squared divided by 17 meters. That's the length of the rope, okay, which is the radius of the circle. All right, so we're looking at 19.1 newtons. Okay, 19.1 newtons towards the center of the circle. Now, here's the thing. We do know force is a vector quantity. And in the last unit, you always had to write which direction it went. If you're solving for FC, the direction is implied. Okay? Centripetal force always has the same direction towards the center of the circle. So unless the question specifically asks for the direction is otherwise implied. Okay? All right. For the 38 meter per second one, 0.9 kilograms times 38 squared divided by the 17 meter radius. All right, so 0.9 times 38 squared divided by 17, 76.44. Is that 4 times bigger? Close enough. 3.99. That's 4. All right. So the effective speed on centripetal force is exponential, right? And I talked a little bit about that yesterday when I said you take the exit ramp, right? If you took it at twice the recommended speed, so if you took it at 120, which you wouldn't do obviously, okay, you would need 4 times as much frictional force to keep you in that corner, okay? And that is not likely to happen. Questions on the effective speed? Okay, what's the effect of radius on centripetal force? Yeah, as radius gets bigger, centripetal force gets smaller because I'm dividing by radius. So if radius gets bigger, I'm dividing by a bigger number, FC will get smaller. Okay, but is it linear or exponential? It's linear, yeah, okay. R is not squared in this formula. If I double R, I'll have half as much centripetal force. Okay, so it's inversely linear, but it's still linear. All right, so the effective radius on centripetal force, so we got a rock on a string, okay, 28 meters per second at radii of 11 and 22. So obviously at the 22 meter radius, we should have half as much centripetal force, okay, according to that formula. So, okay, centripetal force, 0.9 kilograms times 28 squared divided by 11. Okay, so we're getting 64, and then if we do this, we should get, so we got FC equals 0.9 times 28 squared divided by 22. Instead of getting 64, I should get 32. Okay, so 0.9 times 28 squared divided by 22. Okay, half as much. Right, so radius will decrease the centripetal force in a linear fashion. Okay, velocity will increase the centripetal force in an exponential fashion. Okay. Questions on that? All right, so when a car moves around a corner, as we were saying before, okay, an unbanked curve, so that means the corner's flat, so like the corners in town, not an exit ramp. Exit ramps are generally banked. Okay, so if we're just turning in a corner in town, okay, that's an unbanked curve. What keeps you in an unbanked curve is the force of static friction. Okay, so does static friction act on you as an occupant of the car? Not really. I mean, there would be some friction between you and the seat, okay? But in the end, you're inside the car, your inertia wants you to go in a straight line, right? And so if you take the corner really, really fast, you're going to feel like you're being thrown out of the car. There's no force throwing you out of the car. That's where that whole idea of centrifugal force comes from, okay? There's no centrifugal force, there's just inertia, that's all it is. Okay? Your inertia wants you to travel straight, but the car is going to keep you in the corner. Your seatbelt, the door, the holy crap bar that you're holding on to, okay, all of that stuff is acting towards the center of it, or center of the circle. Okay. All right, everybody okay with that idea? No. Okay, so in the last unit, if we were doing a Newton's second law problem, we always had to find out what forces were acting, and then we'd find their vector sum. Okay. Same for circles. But it's easier because we don't have any angles or anything like that. And generally, there's never more than two. Most of the time, there's just one force. Okay? So we just said that for a car going around an unbanked corner, what was keeping us in the corner? Friction, right? Friction was keeping us in the corner. So that means then that friction is acting as the centripetal force. So Fc equals the force of friction. Okay? Fc is not its own force. Fc is provided by other forces. Okay? So the formula for centripetal force is mv squared over r. How do we calculate force of friction?
Force of friction equals
Right, mu times the normal force. Now, because this corner's flat, it's not banked, normal force is equal to what force? Gravitational force. Okay. Would I be able to calculate some things now about this? Like, if I knew how fast a car could go around that corner without sliding, and I knew the mass, well, I don't even need to know the mass of the car, would I be able to figure out what the coefficient of friction was? Or if they told me, here's the coefficient of friction, here's the radius of the corner, how fast could you take it? I could solve for that. Okay? Those are the kind of problems that we might encounter. But what we've just done here, this is the vector sum of all forces. Okay? And this is m times a. Right? So we're still going to have all of that in there. It's just going to look a little bit different in this unit. Right? So what we got a picture of here is a test that car manufacturers often run as a measure of the cornering ability or maneuverability of their vehicles. Okay? It's called the skid pad test. They basically draw a circle on the ground and they tell the test driver, drive the car around the circle faster and faster and faster until you spin out. Okay? Whatever the maximum speed before it spins out is, can allow them to calculate the cornering ability of the car, which is usually measured in G's. Okay? So they find the centripetal acceleration, they compare it to the acceleration due to gravity, and that gives them their cornering ability. Okay? For most passenger vehicles, that number is somewhere between 0.7 to like 0.85 G. What are some things that might affect this number? Absolutely. Center of gravity is a huge one. Okay? And that's not about it sliding, that's about it tipping. Okay? If you buy like a large SUV and you pull down the sun visor, it usually has a warning about danger of rollover. Okay? The taller a vehicle is, the further from the ground its center of gravity is. Okay? And so there's more inertia that's trying to tip the vehicle than to try to pull it out of the circle. The closer to the ground your center of gravity is, the better you will generally corner, because it's more about sliding than about rolling over. Okay? So taller vehicles don't corner as well because they want to roll as opposed to slide.
Can that really counteract it by like a wider base?
Yes, it can. And that's generally why sports cars have a wide wheelbase and a low center of gravity. Okay? Like you never see a tall sports car. Okay? Because they can't corner where the dark. Right? They want to keep them low to the ground. I mean, think of any sports car that's kind of high end. Think of like a Lambo, a Ferrari, a Porsche. They're all, if you stand next to them, they come up to about here. Okay? And that's to keep that center of gravity low. That improves their cornering ability. Then you stand next to a big SUV and you can't see the roof. Yeah. All right. So that's what we're looking at here. Okay, is that static friction acts as a centripetal force. So what we want to look at here is a very common situation for us in Canada. Okay? How fast can I take a corner under ideal conditions, where my coefficient of friction is 0.9, versus icy conditions, where my coefficient of friction is 0.1. Right? So I have 1/9 the amount of friction available. How much slower will I have to go? remembering that it's an exponential relationship. So if I have 1/9, I'll have to go 3 times slower, 1/3. Okay, that's what it should come out to, but let's confirm. Okay, so what we've got is the radius of the corner, okay, and we got the coefficients of friction. Do we need the mass of the car? It cancels. Okay, doesn't matter. All right, so if I'm trying to solve for V, I'm going to multiply both sides by R. Okay, M's going to cancel. And then I'm going to have to what? Square root. Okay, so I'm going to get that V is the square root of mu GR. Mu GR. Mu GR. Okay, that way for every single frictional-based question. All right, so we got V equals then for the ideal corner, 0.9 times 9.81 times 50 meters. That was the radius of the corner. All right, so under ideal conditions, I can take that 40-meter corner at 21 meters per second. Okay, that's like, what, 80 kilometers an hour, something like that? 75, 76 kilometers an hour. Okay, it's pretty fast. Okay. Now, if I change that, and now I'm looking at the icy corner where I have 1/9 the coefficient of friction, okay, that's going to be 0.1 times 9.81, okay, times 50. So I go from 21 to 7. I think that's pretty much what we predicted. 1/3, 3 times slower, okay, as a result of having 1/9 the friction. There's that exponential relationship again. Okay, 1/3 is, okay, the square root of 1/9. Okay. All right, everybody okay with that idea? All right, so that's how we do unbanked corners. Okay. Unbanked corners, the force of friction acts as our centripetal force. Okay. How many people have ever been on a plane? How does a plane turn? It banks, exactly. Okay, planes, they have a rudder on their tail, okay, but they don't work like a sailing ship. Like a sailing ship turns the rudder and the ship turns. Okay, a plane turns the rudder, it can make really small adjustments. Okay, but most of the time, if a plane wants to turn, and you feel this when you're descending, okay, because they'll often circle a bit, okay, the plane will dip its wings. Now, when it does that, what do wings normally provide? When a plane's traveling in level flight, what do the wings do? They what? Level. Okay, they're level, yes, but what are they providing? As the air goes over them, they're providing lift. Okay, so the wings of a plane push the plane upwards. They provide the upward force, okay, by redirecting air over the top of them, okay, that causes that lifting force. If you bank the plane, instead of pointing straight up, now the force of the wings tilts, because the wings can only push perpendicular to themselves. Okay, so if I bank, now I've got a lifting force that's pushing this way. It has a vertical component that's hopefully still enough to keep me in the air, but usually isn't. Okay, and a horizontal component that's going to act towards the center of a circle. Okay, so by banking the wings, I'm going to lose altitude and turn in a circle. So whenever a plane dips one wing, it's going to turn and fall. Does that sort of make sense? But that's how planes turn. They just take that lifting force and they angle it so that it now causes them to turn a little bit. Okay? It'll have a component that acts towards the center. We do the same thing with corners. Sorry, we already did that part. Okay, so we do the same thing with corners. I think, Tyson, you were asking about the NASCAR corners yesterday, right? Okay, so the really steep banked corners in NASCAR, they're ridiculously banked. Okay, what they're doing is taking the normal force that the ground always exerts back on the car, and instead of making it point straight up, it's just like the plane's wings. If I tilt the ground, now that normal force has a vertical component and a horizontal component. Okay, and that horizontal component is going to be directed towards the center of the circle if I make the ground go in a circle. Okay, and that's what will keep me in that circle. The more I bank it, the more the normal force pushes towards the center. There is a point where that will break down though. If you make it too steep, you have to go really fast to stay in the corner, otherwise you'll slide in. Okay? If you tilt too much, gravity will pull you down the slope. F parallel will become really big. Okay? The only way those NASCAR cars actually stay on that corner is because they're going so fast, their inertia pins them to the corner, okay? And the normal force pushes them back towards the center. It's the same thing if you watch any of that indoor biking that they do in the Olympics. Right? The tracks that they have, they're ridiculously banked. They start out on this flat little piece in the middle, and then as they build up speed, they go out onto the corner, and they're practically horizontal when they're biking. Okay? And if they weren't moving, they just slide. When they fall, okay, they slide down the sides. Okay? Because now they're not going fast enough to be pinned to the track. Okay?
It's interesting.
It's what?
It's very interesting to be in it.
Oh, have you been in one?
I'm a BMX racer.
Oh,
So
okay. Oh, yeah. It was
if you
BMX
do
track too.
jokes
Yeah,
like that.
just down there. Yeah, if you fall, you slide into the middle. Okay, that's how they're built, right? They increase your speed, increase your ability to corner. You'd never be able to take a flat corner at the speed you can take a bank corner, right? You'll slide, right? Banking the corner gives you friction as well as a banked force from the corner, right? So this is what I was talking about. Okay, when we bank a plane, the lift from the wings now has a horizontal component that's directed towards the center, a vertical component that no longer balances gravity, so the plane descends. Okay? And the same is true on a banked corner. As soon as we bank the corner, the normal force tries to push a little bit towards the center of the corner. Okay. If we design a banked corner properly, we can eliminate the need for friction. Right? Then that's actually what we try to do with exit ramps or on-ramps. Okay? We bank them so that they can A, take up less space, and B, not rely on friction. That means that under any road condition, that corner will be safe if you take it at the right speed. Right? So they have that recommended speed, that's why the sign is yellow. Okay? It's recommended, it's not mandatory. Okay? But if you take it at that speed, even if it's covered in frictionless ice, you will go around the corner. There'd be a neat trick on frictionless ice, but it would theoretically work, okay, if you took it at the recommended speed. But taking it at the recommended speed will guarantee that you traverse it safely. Okay? Going any faster than that, then you start to rely on friction again, and friction is variable. Okay? In fact, what often happens is when the ice is finally all melted, there's still all the little rocks. Okay? Can you slide better on those rocks when there's no ice? They're like little ball bearings, right? They get underneath the tires and you can slide on the rocks because it's not bare pavement on rubber anymore. All right. So a bank curve viewed from the side is an inclined plane. Okay? So this is what I was talking about with banking the curve makes the normal force help you. Okay? So normally when we looked at an inclined plane, we had gravity acting downwards and we had normal force acting this way, and then we had F parallel, okay? That's all still there. But what we do is we flip it. When we're on top of it and we're using it as a circle, okay, we want that normal force, okay, still pointing this way, to have a component that's towards the center. All the inclined plane stuff we dealt with, they were sitting on the ramp and either moving up or down the ramp directly. There was no inertia involved. When we're doing this on an inclined plane that's a curve, we're moving around the curve as well. And so that means that we have some inertia that wants to go out, okay, go in a straight line. So as a result of that, the weight of the car causes the curve to push, but the inertia of the car also causes the curve to push. So we get more normal force than we would have when we were looking at it this way. Okay, you guys kind of follow me there? Okay. Going around a corner is not the same as sitting on it. Sitting on it, I'll slide into the middle. If I'm moving around it, I can stay pinned to it because I get more normal force because I'm pushing on the corner harder than I would if I was just sitting on it. Okay? So what we get is this normal force right here. Normal force always acts perpendicular to the road. Okay? So it acts straight out. Okay? We'd have this side here, which is gravity because it's vertical. Okay? I'm not falling into the road. Okay? And then this part here would act as my centripetal force because it's directed back towards the center. Right? So actually in this situation, normal force is the hypotenuse and gravity is now the other side. So gravity is smaller than normal force on this one. Okay? Still an inclined plane. All right, so this angle here, the angle of bank, is what determines how much centripetal force I get. The greater that angle gets, the bigger this side of the triangle will become. And that's what pushes me back towards the center. Everybody follow on that? Okay, but the bigger that angle gets, okay, the more likely I am to slide into the middle because I'm not getting as much force keeping me from sliding. Okay, everyone okay with that? Right. How much do we normally bank a corner, do you think? Like, how banked do you think that corner is out there? It's actually usually less than 10. Yeah, like we have this really like skewed idea of angles in society. It's like, oh yeah, you know, we could go up a 30-degree hill. Really? A 30-degree hill is really steep. Okay? Those corners are usually banked 6, 7, maybe 8. Okay? You don't want to bank them too much because they become difficult to maintain, right? Especially if they face north, then they never get any sun and they're harder to keep ice free. So you don't want to bank them too much because some part of them is always going to be in the shade then. So we don't bank them too much. We bank them just enough, okay, that they give a little extra force.
What about when we go down and ski, like a competition?
Okay.
How steep are
It would depend. They are usually pretty steep. Yeah, they could be more than 20, upwards of 30, right? Like it's hard to walk up a ski hill. That's why we've got chairlifts and things like that. Yeah, they're usually pretty steep. All right, I think we'll leave it there, guys. We're 3 minutes out. I gotta wipe down the desks. So if you can clear off your desk so I can come around and wipe it down, that'd be awesome.